Let's explore two different functions and how we can determine their domain and range without having to go through all the necessary steps of graphing it. So for example, let's start with this one here. We've got f of x equals 1 divided by x squared minus x. And if you're trying to find the domain of this function, it's important that we always start back with, well, what does it mean to be a domain? What does it mean to be a function? Well, a function is anything that takes one input to at most one output. So we've got a one input to one output. You can't go to more than one place. So that's what it means to be a function. Is this a function? Well, if I was to put in an input, something for x, like maybe the number 3, would 3 squared get me 2 answers or just one? And it would give me just one. 3 squared is going to be 9 all the time, no ambiguity for certain. So that means that squaring is not going to have a problem with function. If I do a square minus a number, so if I do 9 minus 3, is that going to be a problem? No, not at all. That's going to get me, again, something that's very unambiguous. And then I can do 1 divided by that, and I should get, again, at most one answer. So there's not going to be any problem with this being a function. It definitely will be. But that doesn't necessarily mean that the domain is all real numbers. In other words, it doesn't mean that I can ask just any question or put in any input into here. So let's go back through and break this down. What all do we have going on in this function? Well, we have, as we just explored, a squaring. That's kind of our first step. And then after that, we have a subtraction that we have. Both of those are on the denominator. And then after that, we would do 1 divided by. So we would have some division. And if we're trying to look at what the domain is, all the questions we can ask, we're going to be looking for where might I have some potential problems with questions that I try to ask. So the way that I like to go through this is ask, is there any number that you can't square? And I would say no. I mean, even let's run through a couple of quick examples. Can you square positive numbers? Sure. Negatives? Absolutely. Decimals and fractions? Yeah, fine. Can you do it with, there's nothing you can't square. You can always multiply something by itself. So no problems there. What about subtraction? Is there any number you can't subtract from or with? No, no problem with subtraction. What about division? Is there anything you can't divide by? And this is where we see that that's going to be our problem area for this problem. You can't divide by 0. So this is going to have an encounter where we're going to eventually have a conflict. So let's explore that conflict. When does that happen? When is it that this entire denominator, the thing that we're dividing by, is equal to 0? So we're trying to figure out, when does this happen? Because we don't want to allow it. Well, this is currently saying I have a square minus a number equals 0, and we can do some guess and check, like maybe 0 pops out to us as a number that works to satisfy this situation. But I want something a little bit more robust. Maybe instead of looking at this as a subtraction statement, an addition or subtraction statement, we could look at it in a multiplication statement. Like, we could factor this. We could look at pulling out an x, factoring out an x, and having this be x times x plus 1 equals 0. Now, what's the benefit of looking at things that equal 0 through the lens of multiplication? Well, it's really easy to figure out what everything being multiplied has to be. For example, what do you multiply by to get 0? 0. You multiply by 0. So that means that each of these could be 0 to make the entire thing 0. So let's explore that. X equals 0 and x minus 1 equals 0. Well, x equals 0 is pretty straightforward. X minus 1 equaling 0, we could add 1 to both sides, or logic through that x would have to be 1 for this entire statement to be true. So those are going to be the two places where we have some difficulty. If we don't want the denominator equal to 0, then that means that all of these things shouldn't happen. We shouldn't have x equal to 0, and we shouldn't have x equal to 1. That's great. Now, as far as describing the domain, you could do it exactly as we have over here. So domain could just simply be x not equal to 0 or 1. But oftentimes we'll express the domain in terms of interval notation. So for interval, since we're looking at stretches of numbers that work or don't work, I like to think of this in terms of a number line. So let's draw a number line, and then we're just going to try to exclude where 0 is and where 1 is, because these are numbers that will not work. So we'll put an open circle around them to show that we don't want to include them, and then we can shade in the rest of the number line to show that all of this stuff does in fact work though. So that means everything before 0, between 0 and 1, and after 1. For our interval notation, we're now trying to say, okay, well, what is the interval, this stretch of numbers here, that starts someplace and ends someplace? Well, it's going to start at the biggest, most negative number, there isn't a biggest, most negative number. Maybe negative infinity is what we're thinking, but that's not really a number. It really is kind of a placeholder to say that there isn't a biggest negative number. So we're just going to use this negative infinity with a parenthesis to show that there's nothing we can grab onto as the starting place for this interval. And then it's going to go all the way until 0. But then when we get over to 0, can we grab onto 0 as the ending point? It's not included, so we definitely don't want to use a bracket. We'll use another parenthesis. And you can start to see that we have a mirroring between this interval notation and the number line. And then we're going to pick up right after 0 and go until 1. So it's going to be starting at 0 and going until 1, but not actually starting at 0, starting after 0. So we'll use a parenthesis there, and we'll put a U for union to union and show that these are actually all part of the exact same picture. And then we're going to have another union because we're going to need to pick up immediately after 1. So we'll use a parenthesis 1 to show that 1 is what's drawing our eye, but that we don't start at it, we start after it. And we're going to go until we never stop. So we'll put an infinity here as a placeholder to show that there isn't a positive number, a most positive number at which we're going to stop. And this is a nice way to express our domain. Now, as far as range goes, there isn't a much better way to look at the range of a function other than graphing it. So for this function, if you type it into a graphing calculator or if you plot some points in a table, you're going to see that this is going to come out to something that has a problem above 0. And that's because that's where you're going to have a divide by 0 error. So we'll put some dotted lines there to show that there's not going to be any function above 0. And there's not going to be any function above 1 because we'll have a divide by 0 error there as well. And everything else graphs out as a pretty interesting curve. You get a little bit of this, a little bit of this, and a little bit of this. Now, for those of you in algebra, you'll be learning about faster ways to be able to sketch this graph by just looking at some of the properties. For those of you in pre-calculus and calculus, you should be able to do this already. And if not, make sure you're asking your teacher for help. But you can always, of course, reference a graphing calculator while you're getting more comfortable with this technique. And in the graphing calculator, I can see that the highest point it comes to down here is -4, and that these tails both go towards 0. So let's think about what the range is going to be. Again, the range is going to be kind of everything in terms of heights that this graph has. So I'm going to draw a number line off to the side, and I'm going to shade it in corresponding to where we have heights on this picture. Because, for example, this right here is a height that's perfectly valid on my function. So over on my number line, I'll shade it in. And this is another height that works. And in fact, everything between those heights works. So I've got a lot of shading in here. All of these heights exist. When we get down to 0, these tails don't actually go and touch it. So we're going to need to leave this open because there isn't ever a height of 0 on this graph. But everything above it, we'll shade in. And then we'll put a little 0 here for our notation. And then I have a huge gap in heights. There's nothing in this span right here, but I do pick up immediately at -4. And the question is do I ever have a height at -4? And sure enough, this is a height of -4. So I'll use a closed circle there and then shade in everything below it. So now we can take this entire thing and we can kind of flip it sideways and look at it as a number line, right? Because as a number line, we're really just looking for when is this thing actually starting and ending so we can use our interval notation. This exact same picture started from way before -4 up until -4. So it had all of this. And then it stopped until it got to after 0. So we'll do an open circle at 0 and it continued on forever. So this is really just kind of rotated into this picture, but now we can see what the interval notation is for our range. It's going to start nowhere. It's always going to have gone since we'll use negative infinity as a placeholder, and it's going to go until -4. So then we're going to put in -4 and include it because it's a closed circle. We're going to pick up again, so we'll union that with a parenthesis for 0 to show that there isn't ever actually a height of 0, but that there is a height of everything after 0. And then we'll put a infinity symbol here with a parenthesis to show that that never ends and that there is no highest point on the function. So there we have our domain interval notation, our domain in terms of a number line picture, and our domain in terms of a descriptor. And same thing for our range. We have our range, which would be in terms of the interval notation, in terms of our number line. And if we wanted to do it as a descriptor, we would probably want to use set builder notation. And set builder notation is when we're trying to talk about all of the piles of objects that would satisfy this condition. So we're going to use a curly brace here. This is a symbol you can find above the enter key on your on your keyboard, and it just simply means we're about to pile together everything that works for this situation. So it would be a pile of a whole bunch of things. So we're going to need a placeholder. We'll call it X, and this just simply means all numbers. And we'll give it some conditions. So this is a line that means such that. So we have a pile of things, all of which I'm going to refer to as X, such that these X values are what? Either less than -4, and we'll put not less than -4 like this, let's put X less than -4, or X greater than 0. So let's double check. Did this all work? X is less than -4. Oh, check this out. It actually could be -4 as well. So to include in our pile, we'll put in an equal sign to say it's less than or equal to -4, or it has to be bigger than 0, and we'll close that off. This is a really nice set builder notation. And so this is a good time when you should write down in your notes what this notation means. And so we can put a couple of descriptors here. These curly braces, remember, mean it's a set, or you could think of it in terms of a pile or a collection. It just means that I'm about to group a bunch of things I want to talk about. This straight line here means such that. And then these are all of our conditions. So you can literally write in complete sentences over here, or you could just simply use some of the symbology that you already know through your math classes. So this is a set of all numbers. We'll put that in here, all numbers. X, such that X is either less than or equal to -4 or greater than or greater than 0. And so this is what we would refer to as our set builder notation.